Sì. Adesso passo la parola a Fabrizio Falchi dell'ISTI, che sarà il chairman di questa sessione.
È un gran piacere per me moderare questa sessione. Per prima cosa presenterò Katharina Morik, quindi per rispetto a lei switcho all'inglese. So, it is a pleasure to introduce Katharina Morik. She's a doctor and professor and chair of artificial intelligence at the Technische Universität in Dortmund. She is member of National Academy of Science and also member of Academy of Science and Art, North Rhine-Westphalia. I would like to mention that she is very active in promoting diversity in many respects, including gender balance, but I'm also happy to say that in this session it was already balanced, so it is obvious that she's here only for her outstanding contribution to the field of machine learning, which is the driving force of artificial intelligence renaissance that is going on. And today she will talk to us about research issues and the new German competence centers of machine learning. So thank you very much.
Thank you for the kind introduction. First, I have to excuse myself for speaking English and not Italian, although I had to learn Latin language in school. I'm not able to talk Italian. So, I want to give you a short overview of some of the issues that are similar to your discussion, but are the discussion in Germany. So what we see on the one hand here, it all started with a meeting at our Chancellor, Angela Merkel, where you see that all the people from artificial intelligence and related fields were meeting, and we were discussing half industry and half academia about how to organize the research future and the applications. And then in another picture you see our Minister for Education and Research, and she's holding with me together the sign of my university, because we were starting a center for machine learning. And then you also see our little sign with what is a new center on data science that we have also started at my university. So what I want to tell you is a very short, giving you a frame of data science and artificial intelligence, in which then I focus on machine learning and then on the competence centers that we have now in Germany. And then I come to some scientific points where there are the machine learning challenges. So the big picture on data science, there we have the scientific experiments that create big data. Then we have the big data analysis that delivers data summaries for inspection and also predictions. And then the foundations, of course, are the sciences. In particular, I am working with astrophysical data, but all sciences, and also medical data, but all sciences have large data repositories. And then there is the computer architectures that have to be nicely arranged to collaborate in the analysis and summaries. Then we have software frameworks like the streams or like the cloud computing, like things like that, and the algorithms, and then databases and statistical methods. So in a way, a lot of fields are together in creating what is data science. And I've taken this overview picture of domain expertise, mathematics, and computer science, and you see that without domain expertise, the intersection is machine learning, and if you include, it becomes data science. So I think why is data science so successful nowadays? It is because actually we have a paradigm shift in sciences, right? We no longer only go for inference from first principles, but we have a paradigm shift to empirical science. So here I have just two examples on which we worked in our collaborative research center on extracting information from large data. That's the name of it. The one hand is with the neutrinos that come from a blazar, where you can now, for the first time, we could detect the same outer galaxies event from two different types of experiments. On the one hand, the neutrino, and the South Pole, the 3-kilometer ice shield that delivers data by these little cameras, and on the other hand, by the Cherenkov telescopes. So they two different measurements could come up with the same location in outer space and another galaxy, where we could then observe the dying of a star, so to speak, in more general terms. Okay, so that is that was discovery of stars in other galaxies, and then also we could explain phenomena based on heterogeneous measurements. So, for instance, also the gravitation waves could only be detected because several experiments with huge data sets of a terabyte, terabytes per day could be combined. So, of course, in medicine, we know that data are very important from the genetic data. There in Nature Genetics, we had a publication on the neuroblastoma data. Neuroblastoma is a very dangerous cancer to young boys of until the age of 1 year. And so the issue is also that you cannot talk to the patient. And it is a very small patient with a 1-year-old child, and therefore making personal medicine is extremely challenging, and we are working on that. And there was a publication in Nature Genetics on that. Then, of course, also in other disciplines, for instance, linguistics and sociology, there was a change from a more principled reasoning to the more empirical scientific paradigm. For instance, in linguistics, only since we have managed the very, very large data corpora, we could detect some particular effects in natural language. Okay, so that's about data science. And now to artificial intelligence. Of course, artificial intelligence is quite an old established discipline. We had natural language processing, planning, robotics, reasoning and inference, information retrieval, the World Wide Web. So all these types. And in Germany, the German National AI Research Institute is continuously funded since 1988. So there are permanent positions there, and so that is well captured by many disciplines. So that's fine. And the orthogonal mission is that if you have these traditional AI fields, they can become smarter through machine learning. And that's what you see in all these fields. Maybe the most visible one is on vision, where image understanding made the breakthrough through machine learning. So machine learning, I consider it as a part of computer science. So I think it is a formal discipline in computer science. It's not neuroscience. It is not brain science. It is computer science. That's what I think. And then it is based on data. Data come in streams. They come distributed in the Internet of Things. And you need to store and curate all these data. And machine learning programs have very complex architecture. So they are not just this one step or this one neural network. It is a whole chain of very important processes, from model selection and feature creation and all types of things. So and they are even embedded into each other. That is the rapid miner process that I gave you as an instance there, where within one of the processes of the above, there are embedded processes a level lower, and we have up to 10 levels of processes being embedded into each other. That makes it hard to understand for humans what is happening. That's why I take my time to talk about this. So now let's come to machine learning itself. Machine learning has a very good tradition within Europe. So Yves Quadratov and I helped in that. We together made the first European working session on learning in Paris 1986 already. So we have a good tradition on that. And if you see what the importance is of this subfield of AI, you easily see in the AI index of the Stanford University that actually the conferences on machine learning are the most visited and most important. And what is even more important, they have the highest impact on economy and everything. So it has many, many models. It is not just a little single bit. Of course, neural networks have become so famous because of the game issue. After AI was first defeating the chess masters, now it has even defeated the Go master, Lee Sedol. So that's why they became so visible. And, but there are all these other types, and we should not take one over the other, but they are all equally important. Okay, then there are the application areas, and that's what makes it so important for the impact. So here is one example that I worked on is in steel production. So I did a lot in steel production and in predictive maintenance for other production issues. So model predicted control, which used to be done by pure mathematical means, is now enhancing to become data-based, and therefore what we have done is in real time control the steel cooking, so to speak, and by that save the amount of 40,000 euro per day. It is only a little increase in precision, but a large increase in money because of employing machine learning in real time. Then there is logistics. So you see a little picture of our Dortmund logistics campus, where we have all these nice distributed data collections so that we can use it also in traffic. In the Academy of Science, I'm in the modern mobility working group, where we do a lot on logistics and modern mobility, and I know that there is a tremendous work done here in Italy, in particular by Fosca Gianotti, and that is on mobility patterns and detecting what the mobility patterns in urban societies really are, and then, of course, ruling them such that they use less energy and cost less. Then, of course, medicine and health, information extraction, knowledge graphs, all these are application areas. Then I hope that I convinced you that machine learning is a large field. What is to be mentioned still is that research is still needed. We have achieved a lot in results, but further research is really needed because it is a key to data-driven sciences, it is a key to smart economy, and the need of machine learning specialists is what is really, really the problem within Europe. So we know that all these smart people from other continents move to the United States, and we know that even from Europe people are moving to the United States. What we need is well-educated personnel, and what currently is the situation is that in Europe we educate the good people, and then they move to the States, right? And that is really, really, I mean, if anything is damaging our economy, that is the key point that damages our economy. Okay, so there is a need of machine learning specialists here because only professors can educate the ones that do the research, the ones that create the startups, and the ones that go into the companies to there do the applications using our methods. So all the three things that we need are educated by this very, very small number of machine learning or data science professors. And that's the brittle point. So, okay, so these are the demands. We are in a high international competition. There is a scalability now in demand. We have excellent research by single persons, very few single persons, but that doesn't scale. Then we need to attract excellence from other continents to Europe. We need innovation, transfer, novel business models, and so on. So if we just do a compare, so China is investing $150 billion into artificial intelligence. Germany is investing $4 billion euro into new technologies, where AI is one part of it, and within that machine learning is a part of it. France is 1.5 billion into AI, only AI, not all the other, so it is a different, and then we know that MIT is just investing $1 billion, just one institute, and we know that some Chinese cities have 50 billion per year for making this. Okay, so that's the challenge. Now we come to one of the answers in Germany. So there is already this German research center on AI that has 4 places in Bremen, Berlin, Kaiserslautern, Saarbrücken, and it is funded, so for decades it was the only people that received governmental funding for AI. And they never ever did machine learning. So machine learning has not been funded in Germany by the government. So that was all done by the permanent professorships and European projects. So Europe was very helpful for us so that we could develop. And then there are, of course, Max Planck Institutes, and some are very much specialized on machine learning as well. In Tübingen, for instance, Bernhard Schulkopf has his large group since years. There are now the measurements that are for collaborative research centers. I talk about that in a minute. And then for the infrastructure for data. Some federal states have invested already some money. For instance, Baden-Württemberg has created this so-called Cyber Valley, and Bavaria has created Bavaria Digital, as it is called. So they have created already quite a lot. Now I come to the new funding, that is the machine learning competence centers. So this is now an initiative of German government to, for the first time, invest into machine learning also by some governmental money, and there was a competition, and so there are the 4 centers for machine learning, and I've also taken into the picture the 2 centers for big data, because it really comes together, so that you see this is coverage of the research centers. They have to do research, of course, that's why they are research centers, but they are also meant to do networking, and I'm responsible for doing the coordination of all the 4 centers for networking, and what I aim at is that we make it a more also European network, so that we have a network of networks. That's why I am here, and I'm happy to see you being so well organized in that field. Then to organize summer schools and do transfer to applications. Because what really is important is that we have a center of research in the middle, and then organize around it the startups. For instance, from Dortmund there is a startup Rapid Miner that has become quite famous, but there are others as well, and then comes the next round, and these create centers within other companies. For instance, what you might know only as a pharmacy or is Douglas, but Douglas now has a big data center for online marketing and so on, and that then comes to the more traditional, very large companies, and so these rings around a center are very important to give the economic impact for it. Okay, and then in the end we could have it that if these rings expand, we could cover Germany, and there is already a German platform for learning systems by the government where people can put their material in and so on, and there are working groups working on that. So this is as we have organized it so far. Now let's come to the challenges of the field, the more scientific thing. So on the one hand, we need to make learning more robust. That means that if there is a concept drift, that is, things are changing, when do we realize that we have to change our model as well? Then there is transfer learning. Can we transfer what we learned from one city to another city, for instance? Learning in complex data structures, so what if we put knowledge also into it? Does it help or even be more difficult? Then we could have spatial temporal models and graphical models and so on. Then, in my personal interest, there is a relationship between learning and hardware, so between artificial intelligence and technical computer science. On the one hand, that we do learning on or for restricted hardware, and on the other hand, that we develop hardware particular for machine learning. And then, of course, I know that we share that human-oriented learning is very, very important. So let's see what is with complex learning. There we have, for instance, extracting knowledge from text and exploiting user feedback. Exploiting user feedback means that we have to find a way of interaction with the user, and that we also make active learning, that is, the learning system determines the minimal number of questions to ask to the expert in order to enhance the model. Then using simulations, an interaction between simulation software and machine learning software is, I find quite interesting also, that machine learning software can be the simulation software. That's a long story actually. Tailoring learning based on knowledge. We might, in the Bayesian manner, introduce knowledge into some a priori settings and into regularization of the optimization problem. And then we might also restrict the parameter space. Okay. Then I just go into this because it is the topic of the Collaborative Research Center that I'm leading with 14 projects and a PhD school. And that is that small devices produce massive data streams in the Internet of Things. And then we do, at the little restricted device, we do a data summary and then only submit the data summary to the cloud. And there we do some learning, or we directly learn in a distributed manner from the distributed sensors. So we are working on new machine learning models that require less memory, less communication efforts, and less computing capacity even. So we take our most complex models and make it such that they can work on very, very restricted engines. And then, of course, there is the issue of hardware design, where I just have shown this picture of FPGAs, where you can, with these field programmable gate arrays, we are investigating how to rewrite our algorithms such that they can run there, and if they are successful there, then you can turn it into a chip. Well, sustainability is, of course, it's my true motivation, so to speak. I think that machine learning is what you can use for sustainability. It's the best way to really come to a sustainable thing. And there is one example. You might know Vinton Cerf. He's famous because of his inventions in the 70s. TCP/IP was what he invented, so he's very famous. No. And what he said is Google's most important application of machine learning that was actually in the computing centers. So they could decrease. What you see there is a picture of one computing center of Google, and that is only the cooling of the computer center. So that is the cooling, and that is taking a lot of energy. And by applying machine learning, they could reduce the cooling by 40%. And that is making it sustainable. So actually, Google needs it because they are using a lot of energy, and machine learning can reduce energy. So that's important. But also, we make machine learning itself use less energy. So that is a thing that we are currently doing. What you see there is a microcontroller who uses extremely little energy, but he also has only very little memory, and it even has no floating point. And now, consider probabilistic reasoning without floating point computation. That is something where we thought it cannot be done, and then we have shown how it can be done, and we have proven that it delivers accurate results. So that is, we did it for graphical probabilistic models, and we did a computation that uses only integer numbers and operations, and we are also implementing learning algorithms on FPGA, and what you see there is a little microcontroller that we have produced on our own in the Collaborative Research Center, and it goes with a package to enhance logistics. Okay, so what we could do is really we could do energy saving of complex graphical models. We could compress it to less memory using. Oh no, I will not go into that. We could make it scalable and using only a very, very few things. We went into a new algorithm for calculating integrals, so very lot of mathematics to be done there. Now, why is this so important? It is also important that you can explain what you are doing. Now, as I said, our processes are so complex, and what I wanted to show you just a little bit is that the mathematics behind it is so complex that in a way you cannot explain it. If you could, why does teaching take 4 years to become an expert? So you cannot explain it, but you have to make it explainable afterwards in order to justify it. You have to make it interpretable so that it is easy to be understood, and you have to make it inspectable. Now, that is my belief, you cannot do this by explaining all your algorithms and how they interact. That takes 4 years, or it is wrong. I mean, the easy things to explain are always wrong. So what can you do? Well, you can explain by examples. You have test cases, and then you explain by example what the outcome is. And then, if you really know about your algorithms, then what you can do is something like these things that you have in your clothes. So, where I do not understand how my washing machine really is doing all the fuzzy logic with the water control and so on, I do not understand that. But what I understand is a little thing I have in my clothes, what I can do and what I cannot do. And now what we need to do is we need to develop things like that for our algorithms. And then we can give to the people something where we say, this is what you can do. You can wash until 60 degrees. Do not take more heat, then it will shrink. And something like that we can do with our algorithm. You can use it in that way. Do not exceed it into that, then it will not be accurate. That means that we have to know the bounds of accuracy and all the circumstances under which that happens. And then, with this basic research, we can turn it into something that people understand and that give them a warning or a guarantee. And that's what I think what we should do. That means we translate theoretical proofs into this kind of washing labels. And that is the reason why we need so much research. Because in order to do so, we need to know much more than we know currently. And so what we need is research in data science and artificial intelligence And in machine learning, and then I've shown you these competence centers in Germany that hopefully will bring us further. And what is very important, machine learning fuels good labor for the people. It is possible that due to machine learning, labor can become nicer and become less, actually. That is something we must make clear. It is not that people become unemployed because of AI. It is simply that instead of working 60 hours per week, we could, let's dream a little, work 20 hours per week with a full wage. And there you see where the problem is. Right? It's not a technological problem. And then we can gain scientific insight, and then we can gain more sustainability, because it is not only that we do a prognosis, but we can also do the optimization based on the prognosis so that we have less traffic, because we have a better organized traffic due to our movement patterns that we know. And then, of course, machine learning must give guarantees for the learned models in order to have people rely on that. Okay, so this is what I wanted to state. Further research is urgently needed.
Thank you, Katharina. It was very interesting, and I think that it will be of inspiration of the next talks.